Okay, so what did we say P sequence was? P sequence? 1 over I to the P. So what is constant and what is changing there? The P is constant. For a particular P sequence, you have a constant value of P, right? And the I is your index, right? 1, 2, 3, 4. That's how you generate the terms of the sequence. I is 1, I is 2, I is 3, I is 4. Okay, and then we had geometric sequence, which was R to the I. What's constant here? R is your base, that stays constant, and then I again. So R to the first, R to the second, R cubed, R to the fourth. So to get the next term in the sequence, you just multiply the last term by R, right? Because you always get one more R multiplied as you march down the sequence. Okay, so then we want to talk about just analyzing sequences in general for convergence and divergence. So we want to be on the lookout for our geometric and P sequences. Okay, when does a P sequence converge? What do we find out? When P is greater than 0, positive, right? Greater than 0 or positive. When does a geometric sequence converge? When R is between -1 and 1. Okay, so we analyzed those last time. So we're always on the lookout for those. All right, so use function limit notate techniques. So think about your sequence as a function, and you're thinking about like letting your independent variable get very, very large. Does the limit exist, right? Thinking of it as a function. So properties of rational functions, right? So this is like back in pre-calculus, you did the horizontal asymptote problems. Is there a horizontal asymptote to a rational function? If there is, then that would be the limit of your sequence. Okay? And then there's another technique called L'Hopital's rule, which says that if you have a function, say f of x over g of x, and you're looking at as x gets large, if that is, so if f over g goes to infinity over infinity or 0 over 0, so meaning if you take the limit of f and g separately and they both get infinitely large or they both go to 0, then you have the setup for L'Hopital's rule, and L'Hopital's rule says that that limit is the same as the limit of the quotient of the derivatives. So you take the derivative of each, and you get a new quotient. Well, the limit of that quotient will be the same as the limit of our original one that we're analyzing. Okay, this is not the quotient rule, right? This is not the quotient rule. This is what a lot of students would like to be the quotient rule, okay? But it's not, right? The quotient rule is more complicated. But in L'Hopital's rule, you just take the derivative of the top and the derivative of the bottom. You get a new fraction. The limit of that new fraction has the same value as the limit of your original if you have the situation where both f and g go to infinity or both f and g go to 0. These are called indeterminate forms. And they can be anything. These limits can go to infinity, it could go to 0, it could go to a constant value. That's why it's called indeterminate. Because it depends on the case. It depends on what your functions f and g are. These situations could be anything, and then you can use L'Hopital's rule to help you figure out what it is. Questions on that? So that's another technique that we'll have for analyzing convergence or divergence of sequences. Question on that? So it's kind of like we have this toolbox, and then you come to a problem, you've got to figure out what's going to work. All right, just listing out the first several terms. So we did that last time in class. Just, list out the first several terms. Take a look at it. See what's going on. All right, general algebra. Sometimes you have to do some algebra. Stuff from pre-calc all comes into this. And then just deductive reasoning and logic. Okay, so all these are all parts of the things you bring to the table when you're trying to analyze these sequences. So I think you have web work on this stuff due at 5 or midnight? Tonight's midnight, okay? So maybe you've gotten some start on that. You've been able to do some of them, but after some examples here, you'll be ready. Okay, so that's our kind of what I call the toolbox for sequences. Toolbox for sequences for analyzing for convergence or divergence. Okay, so while I take attendance, you can work on these. These are all sequences, and we got to figure out, as I gets large, does the sequence converge? Meaning, do the terms get indistinguishably close from each other, or does something else happen, diverge? Okay, go. Okay, let's see how you guys did. Angel, tell me about the first one. You.
I said that the first one was divergent. I used the geometric sequence rule.
Right?
Because since it's not greater than -1 or less than -1, I said it was divergent.
Okay, that's right. So it's not that it has to be less than 1 or greater than -1. It has to be both.
Right.
Yeah, it has to be in that interval. Okay, but yes, diverges, because this is a geometric sequence with what? R is less than -1. What's this going to do? -4, +16, -64, plus whatever. And it's just going to keep getting, it's going to alternate between negative and positive and just keep getting bigger in multiples of 4. So clearly this is not honing in on a particular value, right? So it's a geometric sequence with R less than -1. Okay, how about this next one? Calvin. Converges, okay. Uh-huh. Okay, so yeah, let's look at the value taking the sign of. So what, as I gets large, what happens to that? Yeah, David.
It goes to infinity over
Okay.
infinity.
Yeah, you could use the L'Hopital's rule. That's okay, but there's a quicker way to do this one. So yes, it is infinity over infinity. L'Hopital's rule will work. You actually have to do it twice. But there's a quicker way. Yeah, Jeffrey.
So can you just divide the first terms?
Yeah. So this is like a rational function that you like these problems you saw in pre-calc, where you pick the leading term of the numerator and the leading term of the denominator. And as I gets big, those are what's gonna have an impact. -7 when I is really big has really no impact here. So what happens to this fraction as I gets really large? It goes to 1/3. Do you see that? If the degrees are the same, you're going to take the ratio of the coefficients, because any smaller power of I is going to fade away when I gets really big, right? The biggest powers of I are the ones that are going to still be around when I is a billion, a trillion, etc. Okay, so that goes to 1/3. So as that argument of sine goes to 1/3, what does the whole sequence go to? Converges to sine of 1/3. So that ratio goes to 1/3. So then the whole sequence will just get closer and closer to sine of 1/3. So instead of it keeps getting smaller, that's not necessarily. Maybe they're getting smaller, but it's not like they're getting smaller to 0. It's approaching 1/3. Okay, so we can say Um, so we're looking at that. We're looking at that ratio, that rational function. We're analyzing that rational function, and saying that it goes to 1/3 as I gets large. Okay, next one, 1 over square root of I. Shane. Converges to 0, and why? Okay. Yep. What kind of, do you recognize what kind of sequence that is? 1 over I to the? Yes, it's a p sequence, right? So yeah, you're absolutely right. As I gets large, this will get infinitely large, which means the whole fraction goes to 0. And then we could also just say this is a p sequence. And p is greater than 0. Because p is a half. Are we good? All right. Alexandria, how about this next one? 1, 0, negative 1, 0, 1, 0, negative 1, 0. Which one? Converge? To what? What did that converge to? What? Diverges? Yeah, because why? So I'm not going to write it out. But the terms do not get infinitely close to each other, right? They just keep jumping around, right? Again, convergent means that the terms, as you go throughout the sequence, you're honing in on a particular value, getting infinitely close to a particular value. This will never do that. This will never do that, okay? Next one. So how about this one here? Tegan. Okay. Because? Yeah, so we can start the same way we did this one. We can look at what's happening here in the ratio. So what happens to that rational function? What do we look at? Megan, what do you think? So when we look in the parentheses there, inside under the square root, what do we look at? Yeah, Shani? Yeah, okay. And so tell me about those. Right? Right? Yeah, I mean, so that ratio then is I over 6, right? I over 6. I to the 4th over I cubed is like I over 6. So when I gets really big, it's going to get big, right? So I over 6 just keeps getting bigger and bigger. And square root, I mean, that slows it down a bit, but it's still going to get as big as you want it to get. So this diverges. Again, analysts, we're doing rational function analysis there, right? Analyzing that as a rational function, looking at the leading terms. All right, next one. I to the minus 4. Michaela, did you get this one? Okay, good. Yeah. Okay. Good. Converges to 0. Because this is a p sequence, and p equals 4, which is greater than 0. Okay, next one. Pi to the I over 3 to the I. Ashlyn, did you get this one? What's that? No, because our that would be a little. It's not going to help because we're going to keep. So these are exponential functions. When you do the derivative of exponential functions, you just keep getting exponential functions. So L'Hopital rule won't work. We need something else here. So there's something we want to do first before we start this one. We can say it's equal to what? Yeah. Yeah, pi over 3 all to the I. And then Trey, how does that help? Does that, what now? Because it's positive? So what kind of sequence is this? Okay, but what kind of sequence is it? Geometric, right? Geometric with r greater than 1, right? Pi over 3 is just a little bit bigger than 1. So this diverges because of the geometric sequence. Okay, this next one? All right, so we really should talk about what exponents mean. What does 3 to the I mean? 3 to the I. So when you look at that, you think what? So when you see 3 to the I, you have to have a clear image of what calculation that is, what computation that is. What does it mean? Right, it means 3 times 3 times 3 times 3 times 3, and then there's one more detail to this. Yeah, so how many 3's are there? I, number of 3's. That's what 3 to the I means. It means take I number of 3's and multiply them together. So then what would 3 to the I plus 1 be? What would 3 to the I plus 1 be? How many 3's? How many 3's compared to this many 3's? One more, right? One more. So I could say it's 3 to the I what? Times 3. You see that? So if it's I plus 1 number of 3's, then it's like I number of 3's, and then times one more. Converge or diverge? Does this converge or diverge? Why? It's not 9. So you want to combine these? Yeah, it's not 9 because you have I number of 3's and then times another 3. And you have I number of pi's. So how does this compare to the one above? It's just 1/3. It's just all this is all the terms are 1/3 of this one up here. You see that? It's the same sequence, just each term has 1/3. So this diverges. It's the same reason. It's geometric. It's almost the same sequence. It's just all the terms are 1/3, but then you just need 3 times as many to reach the same large number, right? But you never run out, right? You never run out of terms in your sequence. So this is also geometric with r greater than 1. Diverges. All right, any questions on these? Let's see, we got 2 more practice ones here. Before I erase, last chance, questions. Okay. All right, so here's a couple more. So we're going to write out the first 3 terms, and we're going to analyze each sequence as convergent or divergent. So write out the first 3 terms. Okay, so what about 2? Let's just do it separately. What about 2 to the I? 2 to the I, just by itself. Diverges, right? What kind of sequence is that? Geometric with I greater than 1. What about 1/2 to the I? Geometric converges or not? Converges. Okay, so we've got our terms are going to be the terms of a divergent sequence plus a convergent sequence. What will win? Diverge, right? So you're adding you're making it bigger than a divergent sequence, right? So this is so this is divergent, and then you're making the terms even bigger than that. Now by a little bit only, and that gets smaller and smaller, but still, it's diverges, right? Because this is essentially diverges since. So really, what's important here is the 2 to the I. Adding a little bit more, even if it's very small, this will get small, but you're still, which is, what is this, geometric with, do you have a question, Jesus? What's that? No, yeah. Yeah, if you're strictly adding 2 together and one of them diverges, well, okay, I'll take that back. If you had 2 that were divergent and one was positive and the other was negative terms, then you might get a convergence sequence. But if one converges and the other diverges, it will always diverge. There's no way that can converge. But it might be true that you could have individually divergent sequences that you added together, and one was positively convergent, the other was negatively or divergent, and when they add them together, then you get something that converges. That might be possible, but this will never converge. Okay, what about this one? How are we going to do this one? 3i plus 5 over ln of I. Any technique we have for this one? Yeah, this is a good one for L'Hopital, right? Because we don't have a rational function. ln of I is, not a polynomial. So we've got infinity over infinity if we think about I getting large here. So we can take the limit as I goes to infinity of derivative of the top is 3, derivative of the bottom, or I, so that equals 3i. Converge or diverge? Of course diverge, right? Of course diverge. This gets larger and larger. So this diverges by L'Hopital's rule. Questions on these? Okay, so then you saw in your written homework, and then if you've started the web work, these things called factorials, right? This doesn't mean 4, right? 4 factorial means you start with a number, and then you multiply down by whole numbers always until you reach 1. So 4 factorial means start with 4, then times 3, times 2, times 1. So 4 factorial is 24. Okay, by definition, 0 factorial is 1. It's not 0. Okay? So that's another discussion for another time, right? That's 6 factorial, write it out, find the value. Go, write out what 6 factorial is, find the value. Okay, great. All right, so Sydney, what's that? 6 times 5 times 4 times 3 times 2 times 1, 7, 20. All right, what about this? And let's, in fact, let me change it. Oh, no, I shouldn't change it. Okay, so 28 factorial over 25 factorial. So we don't want to write out what 28 factorial is, or 25 factorial, but we can write out something that doesn't kill our hand and represents it. So how can we show what 28 factorial is? We can do 28 times 27 times 26, maybe just a couple more, 25 times 24, and then, so you're going to say dot, 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 and when does it end? 1. So we can write times 3 at the end, 3 times 2 times 1. Instead of writing out all 28 numbers, we can do that, and that represents 28 factorial. And then what do you notice about 28 factorial? What's that, Harrison? It has 25 factorial in it, right? So every factorial has as a factor all the previous factorials. Do you see that? So here is, right there, hidden within 28 factorial is 25 factorial. So what happens when we divide? So if you divide by a lower factorial, then you're going to remove that part of the higher that portion of the higher one. So what is this equal? 28 times 27 times 26. Do you see it? So 28 factorial over 25 factorial is just those three numbers multiplied together, because it's like you take the 25 factorial that's part of 28 factorial and you divide it away, right? It goes away if you divide by 25 factorial. Okay, so now what would this mean? So here's a sequence made up of some factorial expressions. So write out the first three terms of this sequence. Write out the first three terms, right? What is the first three terms? What you get when I equals 1, what you get when I equals 2, and what you get when I equals 3. That's the first three terms. See if you can do that. Ada, did you get the first term? Was it? Okay, 1 factorial over 3 factorial, which is 1 over 6. Did you get 1/6 for when I was 1? You should have. I is 1, then you get 1 factorial over 3 factorial, which is 1 over 6. Okay, second term. 3 factorial over 5 factorial, which is 1 over 20. 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. We get the same thing. The 3 factorials go away, but now you've got 5 times 4 in the denominator. Next one. So it's 5 factorial over 7 factorial, which is 1 over 42. Is this making sense? Okay, so now let's simplify this. Okay, let's simplify this. What is 2i minus 1 factorial? How could we write out 2i minus 1 factorial? What would the first factor in that be? What's the first number we multiply together in 2i minus 1 factorial? Right, so factorials are a product of lots of numbers. What's the first one in 2i minus 1 factorial? Megan's got it. 2i minus 1, right? The first number is always the number of what you're doing. Okay, and then how do we get the next one in the list, or in the next factor? How do we get that number or that number? Subtract 1. So what would it be? 2i minus 2. Make sense? And then it's going to go all the way down to what? When do we stop multiplying? No, not I. When do we stop multiplying? It's the same place we stop multiplying in all factorials. All factorials, when do you stop multiplying? What's that? Where do they all end? Every single one. 3 times 2 times 1, right? So you're always going to end up at 1. Okay? And then now, so you write the denominator. So 2i plus 1 factorial. You write that out. What would that be? Write out what 2i plus 1 factorial would be. Langbo's got it. Carter, can you tell me? Yeah. It's not. Can you tell me, I want to expand this. Tell me what this means. I want to write out the denominator. 2i plus 1? Two I. All the way down to 3, 2, and 1. All the way down to 1. Okay, so what does this become? So we can simplify that. When you do, you've got things right. The 1s can go away, the 2s can go away, the 3s can go away. Until what? What do we have? Michael? We get the same kind of effect that we have here, right? So what will be left? So did you notice we did 2i plus 1, then 2i, and then what happened? What happened started here? What's that? Right, we go with the same as on the top. So then how can we simplify this? 1 over. Tell me what the denominator is. 2i plus 1? 2x. So this original expression, this original sequence I gave you is the same as 1 over 2i plus 1 times 2i. So we should, if we did I equals 1, 2, 3, we should get the same terms we get here. So when I is 1, do we get 1/6? Yep, because we get 3 times 2. When I is 2, do we get 1/20? 5 times 4 is 20. That's right. So this is the exact same sequence as that one because we just did the math and we simplified it. So we get 1 over 4i squared plus 2i. Converge or diverge? Clearly converges, right? Why? This is like a what? This is like a p sequence with p equal to what? With p equal to 2, and then it's actually the denominator is even bigger than that, right? So it's bigger than a p sequence with p equal to 2 in the denominator, which makes it smaller, which makes it certainly also converges. So this is a convergent. It's not a p sequence, but it's like we can compare it to a p sequence, right? We say all these terms are smaller than 1 over 4i squared because the denominator is bigger. See that? Let's write that out. So 1 over 4i squared plus 2i is less than or equal to 1 over 4i squared for all I. Therefore, the sequence that we have, what is convergent by comparison to a p sequence. So converges by comparison to p sequence with p equal to 4, p equal to 2. That's what we mean, that's this comparison. So 1 over 4i squared plus 2i isn't really a p sequence. A p sequence is always 1 over i to the p. But because all these terms are less than the p sequence 1 over 4i squared, because you're adding a 2i in the denominator, you can say it also converges by comparison because all your terms are less. So if your terms are all less, then that's going to converge as well. What if you had something that all the terms were greater than a convergent sequence? Will it diverge? Will it converge? You don't know, right? So if you have something, you have a convergent sequence, you have another sequence, all the terms are greater than a convergent sequence, who knows, right? It might converge, it might diverge. But you can't say definitively like we